Okay, hi everybody. Hope you're doing okay today. We're going to be talking about the comparison of addition and substitution reactions. If you remember, alkanes underwent substitution reactions, but we are going to be comparing. So alkanes underwent substitution reactions, and we're going to be comparing that to the type of reaction that alkenes mostly undergo, which is addition reactions. So as you can see, the most common reaction in alkanes involved the substitution of an H out and one of the A or the B attached to the carbon chain. And so we did, we mainly did this as halogenation. Okay, so that's what we basically have seen so far. So this, at B, the most common reaction in alkenes is addition. And so what we're going to actually do is break the double bond. In other words, break the pi bond of the double bond. And that's going to be the part that is broken. The sigma bond will remain together. So here's going to be our sigma bond still sitting there, and it's the pi bond we're going to break, and we're going to break the A and the X apart, and the A and the X, as you can see, are going to both become part of the carbon chain at the place where the pi bond is broken. Okay. So let's see if we can get into some of the nuts and bolts of what this looks like. Yes, we are going to be forming two sigma bonds, and this reaction is favorable because sigma bonds are stronger, and it is also the formation of a saturated molecule of further saturation. In other words, remember that when we have something that is unsaturated, that means we have multiple bonds, like double bonds and triple bonds. But if we break the pi bond of the double bond and put in two new groups attached, now we're going to be taking into account that we're using up some of that unsaturated nature of it. Okay, so we are going to have something called a polar addition reaction. Okay, so alkenes, because they readily react with either chlorine or bromine, are going to respond well to the addition of a halogen. It's dissolved in some sort of solvent, which is added in small drops. And usually with alkenes, this reaction is instantaneous at room temperature, and we don't need a catalyst required. If you remember, the addition of a halogen to an alkane required that we had some energy provided so that it caused the reaction to happen. So in particular, let's put a star next to this one, the addition of bromine can be used as a chemical test for the presence of unsaturated. So in other words, for the presence of alkenes. And so what will happen? Let's take a look at that. A bromine solution is a dark reddish brown sort of color. As we add it to an unsaturated compound, the product that will be formed is a colorless product. So as it's added to an unsaturated compound, the color will disappear if the compound happens to already be saturated. In other words, if it was already an alkane, the color will not change. Okay, and so that's going to be one of the things IB likes to test about. So you should make note of that particular part of the notes and the reactions. Okay, so let's go take a look at hydrogenation. That first one was halogens, so halogenation of an alkene. Now we're going to go to hydrogenation, and this will be where we are causing the alkene to gain hydrogens. I feel like I should go ahead and step back and go draw in the reaction type that you might see for the halogenation. So we can draw in a halogenation that would look overall like, let me make sure I can write, like this, CH3, CH, which would have a double bonded to a CH2, and then we could have added to it the chlorine, and because it's highly reactive, it will automatically break apart, and we would be left with the CH3 single bonded to CH, which now would have a chlorine here, and it would be bonded to the CH2, which would now have a chlorine here. That's what we're talking about for halogenation. So when we get started talking about, well, what about hydrogenation? So hydrogenation, in other words, is the addition of hydrogen. So this requires more activation energy, so we need to add a catalyst. And you are required not only to know about halogenation, but hydrogenation as well. And so you need to know that the catalyst can either be platinum or nickel. And so to add any hydrogen, H2, to an unsaturated hydrocarbon, we're going to do it in the presence of that catalyst. And basically, it is a way where we can take margarine, which is unsaturated double bonds inside margarine, inside vegetable oil, and change it over to something that's healthier with fewer double bonds. A type of reaction that shows a hydrogenation is if we have ethene, CH2 to CH2, and we are going to add in hydrogen. So we would have some hydrogen added here, and we would need to show the catalyst over the top of the arrow, and that would lead to an overall CH2 now with another H added onto it, and CH2 also with another H. So in essence, what we come out with which is an alkane, CH3 to CH3, just like that. Okay, so what about if we add water? In other words, we are doing a hydration reaction. This is going to be the addition of water. And so H and OH is what's going to be added in the presence of an acid catalyst. And so the question often is, well, what is the acid catalyst? Many times we just write the acid catalyst as H plus. Oftentimes, though, we might just say that the acid catalyst is H2SO4. That is a commonly used acid catalyst. It is used as the electrophile. Let's make sure that we are defining electrophile. The word phile means love or to love or lover. So if that's an electrophile, that is an electron lover. So that must be something that has positive charges in it so that it is attracted to electrons to be able to initiate the reaction. The products, as you're going to see, are going to add up to an alcohol. So this is how we can industrially make our own alcohols using alkenes. So let's look at a type of reaction in which that happens. Here we have our ethene, and we are going to want to add some water to it, and I'm going to on purpose write it as HOH. We will have an acid catalyst, which we will provide as a part of this reaction, and we will get, as a result, the CH2 with an H added to one side, and now an OH added to the other side. So we have just now made ethanol instead of just keeping ethene, excuse me. Okay, so that is the common reaction type for the addition of water. We can use the addition of water to an alkene to form an alcohol. All right, so the next part is going to be the addition of acids. What happens when we add an acid to an alkene? And so we're going to, again, be having one carbon receive the hydrogen and the other carbon receive the other or the remainder of the acid. Usually the acids we use are hydrogen halides like hydrobromic acid, hydrochloric acid, hydroiodic acid, or sulfuric acid. So oftentimes what you'll see again is the ethene, CH2, double bonded to CH2, and let's say that we add some hydrogen chloride, so hydrochloric acid to it, then we would end up with the CH2, which now has another hydrogen attached to it, bonded to a CH2, which now has the chlorine attached to it. And that is your reaction there. This is a highly reactive, electronegative containing molecule, the hydrochloric acid and the hydrobromic acid. So you're going to find readily changing and reacting situations going on. Okay, so we have our 4 basic reactions that you are required to know and be able to use. So what we need to talk about is what happens if, so far what we've done is we've used symmetrical reactants or reactant, as in we've used ethene, where the double bond makes the atom symmetrical. What about if we have unsymmetric addition reactions? So the symmetric situation is where we have at least one of the reactants that is symmetric. So we would have, for instance, the CH2 double bond to CH2. It's the same on both sides of the double bond, and it wouldn't matter what we add to it. Let's just say, what if we add some HBr, which is definitely asymmetric, but it will give us only one possible product. So in this case, it gives us the CH3 CH2 Br. So that would be the bromoalkene, or alkane, excuse me. So what about if we have an unsymmetric? In other words, both reagent and alkene are both unsymmetric. Then we might have two products that are possible, and these two products are called regioisomers. If the reaction gives only one of the two possible that is called out, then we're going to call it regiospecific. If the reaction gives mainly one product, we call it regioselective. These are not terminologies that you are going to be tested on, so this is going to be okay for you to know about it, but you won't be tested on the terminology. Okay, but we do have a rule that applies to this situation. And the name of this guy, who is a Russian chemist, is called Markovnikovs. And in Markovnikovs' rule, we need to have two unsymmetric or asymmetric reactants or reagents. So here is a good example. We might have let me make sure I have my pen, CH3 bonded to a CH, which is double bonded to a CH2. And then we might be reacting it with some molecule that is, and let me just use an actual one. Let's just use, for our example, let's just use water. So let me redraw that, CH3, CH2, double bonded, that was wrong. Let me erase. That should be just CH, double bonded to CH2, and we're going to make it react with some water. Now, the reason why this is going to come out differently than we had it before is simply because both of the reactants are asymmetric. And so the water is still going to require us to have, if you remember, water required an acid catalyst. And so what we're going to need to do then is we're going to need to understand what the two possible products might come out to. And then we're going to talk about which one is the one that in this case is going to be regiospecific. The two possible products would come out to then CH3, CH with an H here and a CH2 that now has the OH attached to it. The other way this might come out is that we would end up with a CH3 bonded to a CH that has the OH attached to it, and then that's bonded to the CH2, which becomes the CH3 when we have the H on it. And so the question becomes, how do we know which one is going to be regiospecific? In this rule, we want to put the more electronegative component. In this case, this one is the more electronegative component. And we want to have the more electronegative component be placed on the hydrogen that has more ability to spread out the electronegativity. And that's going to be on the central hydrogen and not on the ending hydrogen. We can summarize that as when an unsymmetric reagent adds to an unsymmetric alkene, the electropositive part of the reagent bonds to the carbon that has the greater number of hydrogen atoms. And that means that the more electronegative part bonds to the carbon with less number of hydrogens. You are going to have to be able to explain why. And once again, the more electronegative portion of the asymmetric reactant is going to be able to be better have its electronegativity spread out or delocalized over more carbons by placing it on the central carbon. So you must understand why Markovnikov rule applies, and that is because we have two unsymmetric reagents. Okay, when we talk about exactly how does all of this happen, we start to talk about the electrophilic addition mechanism. That's what this is called, and this is basically the steps of the reaction. So we need to define a couple of things. And the first thing that we need to define is what exactly is happening in these polar reactants. We've already talked about pi electrons are more exposed, so they're easier to attack, and so they're easier than the sigma bond, and they're easy to be attracted away from the double bond. So the supplier of the pi electrons can be attracted to an electron-seeking reagent. And so we're going to take a look at, well, what do we mean by those two things? So we have two types of terminologies. The first terminology is the electrophile, and the second one is the nucleophile. And so you're going to see these referred to a lot. And so you have an asymmetric reagent, and it is made of the electrophile part of things, and it's bonded to the nucleophile part of things. And when you break those two apart, you will end up with the thing that is positively charged, and that's going to be the thing that is attracted to other electrons. And you're going to have the thing that is negatively charged, and that is going to be the thing that is attracted to the positive portions of the compound. And so you might have something like hydrochloric acid, which is going to undergo heterolytic fission. Heterolytic, let me try to spell, lytic fission. And the heterolytic fission is going to break apart incorrectly, fission, let's spell it right, or not incorrectly, but unevenly. So as you can see, the electrophile ends up with no electrons, and the nucleophile ends up taking the electrons with it. So that's how that's going to work out there. So we're going to be able to then talk about, well, what exactly is happening as these two things break apart here. So we're going to talk about some examples of when we are adding acids, specifically, or water, or things that are unsymmetric, in other words. So we're going to specifically talk about the addition of acids and the addition of water. So let's go ahead and get started. So the first step we're going to have here is the attack by an electrophile. So let's say that we have already broken apart our acid, our HCl, or we have broken apart our water into the two parts. If you remember, the water part has to have the hydrogen as a catalyst, and that's going to be what causes the reaction to get started. So let's just pretend for just a minute what exactly happens here. So we have something called resulting in a carbocation, a positively charged carbon. So for instance, you will have the electrophile portion of the acid or the water attacking the double bond of between the two carbons, specifically attacking the pi bonds. And what you're going to end up doing is you're going to end up breaking the pi bond and adding one hydrogen onto one side. And so what has happened basically then is that you have had two electrons. These two electrons have gone and only are connected to the carbon now, leaving this other carbon with the two hydrogens attached to it electron deficient. So it's actually positively charged. So this hydrogen is actually now attached in this location here, and momentarily we are going to have a positive carbocation. Carbocation is what that is called. Sometimes you will also hear it called a carbocation. Okay, this part is bond breaking, so it is the relatively slow step. It is bond breaking, and it is caused by this interaction of the electrophile being attracted to the electrons in the pi bond. Okay, so it is attracting the electron, it's coming near the protons, so it uses both pi electrons, which is why you see me circling that one set of electrons there. It's using both pi electrons. Okay, so as we've seen, the other part of the carbon acquires a positive step or a positive charge. And so then we have the second step of what exactly is happening. And so now we're going to have the addition of the nucleophile, which is the negative side of things, being added onto the carbon. So they're doing it in my notes here with HCl and H2SO4 and water. So here we're going to go ahead and write out the whole thing. I'm going to have and I did not want that. Let's get rid of that. So we're going to have the ethene start with being attacked by the electrophile, the hydrogen. And these two electrons are going to be going to the hydrogen. And what we're going to form first is the carbocation or carbocation, either way you put it, and then that carbocation is going to react with the nucleophile part of things, in this case the chlorine ion, which is this ion here, and that nucleophile is going to add itself onto what now is the carbocation, and we'll end up with the CH3CH2Cl. Okay, and the reason why I didn't worry about Markovnikovs rule here is because both of my reactants are not asymmetric. Only one of them is. So the same thing happens, okay, over here with the H2SO4, and the same kind of attraction of pi electrons are happening here. And then we come out with the same carbocation. Again, that's a 3CH2 plus. But this time we're going to add to it the negatively charged S, and there's the O is the negatively charged, and then we have a SO3, and there's an H here, and it is written funny because of the position of the negative charge there on the H2SO4. So what we end up with is CH3 CH2, and what is bonded there to that carbon is the OSO3H, and that's what you end up with there. And finally, we end up taking a look at water, and we have the water being attacked by the nucleophile just like before. And we have the electrons going to the electrophile going to the electrophile, and we end up with our carbocation. And that's going to be the 3. There's our positive. And this time what we're going to add to it is the OH, which is the negative over here by the oxygen. That's our nucleophile, and we end up with CH3 CH2OH. And that is the kind of thing that you're going to see for alkene reactions, everybody. Let's just check and make sure that we've gone far enough. And so let me clear this. And we will go more into Markovnikovs rule, even though I have talked about it already. Everybody have a great day.